Welcome back. Today we will discuss ring homomorphisms, ideals and quotient rings. In abstract algebra, a ring homomorphism is a function between two rings which respects the operation of addition and multiplication. In this session, we briefly discuss ring homomorphism. We will also discuss ideals. An ideal is a special subset of a ring. The ideal conceptually generalizes the property of certain subsets of the integers such as even numbers or multiples of 3, that the product of any element of the ring with an element of the subset is again the subset. The product of any integer with an even integer is again an even integer. An ideal is therefore said to absorb the elements of the ring under multiplication. We also describe quotient ring. A quotient ring, also known as factor ring or residue class ring, is a construction quite similar to the factor groups of group theory. One starts with a ring R and a two-sided ideal I in R and constructs a new ring, the quotient ring R by I. Ring homomorphism. Definition: ring homomorphism. A function phi of a ring R into a ring R dash is a homomorphism or ring homomorphism if phi of A plus B equal to phi of A plus dash phi of B and phi of A star B equal to phi of A star dash phi of B for all elements A B belongs to R. Remark: in the first equation, the addition A plus B on the left hand side takes place in R, while the addition phi of A plus dash phi of B on the right hand side takes place in R dash. In the second equation, the multiplication A star B on the left hand side takes place in R, while the multiplication phi of A star dash phi of B on the right hand side takes place in R dash. Definition: isomorphism of rings. An isomorphism or ring isomorphism phi of a ring R with a ring R dash is a one-to-one function mapping R onto R dash such that for all A B belongs to R, phi of A plus B equal to phi of A plus phi of B, phi of A into B equal to phi of A into phi of B. Briefly, phi is an isomorphism from R to R dash if it is a homomorphism from R to R dash, that is both one-to-one and onto. Definition: isomorphic rings. Two rings R and R dash are isomorphic if there is a ring isomorphism from R onto R dash. Example 1. Consider the rings set plus dots and 2 set plus dots. Verify whether the map phi from set to 2 set defined by phi of x equal to 2x for every x belongs to set is a ring homomorphism or not. Is it an isomorphism? Solution: since phi of x plus y is equal to 2 into x plus y, which is equal to 2x plus 2y, which is equal to phi of x plus phi of y, condition 1 of homomorphism is satisfied. But if both x and y are not equal to 0, phi of x into y equal to 2 into x into y, which is not equal to phi of x into phi of y, which is equal to 2x into 2y, which is equal to 4 into x into y. So that condition 2 is not satisfied. Hence, phi is not a ring homomorphism, hence also phi is not an isomorphism. Remark: if we consider set and 2 set as two groups, then since condition 1 is satisfied, phi is a group homomorphism. Also, since phi is one-to-one and onto, it is a group isomorphism. Example 2. Evaluation homomorphism. Let f be the set of all functions mapping the field of real numbers into the field of real numbers. It can be verified that f plus is an abelian group under usual function addition f plus g of x equal to f of x plus g of x. We define multiplication on f by f into g of x is equal to f of x into g of x. That is, f into g is the function whose value at x is f of x into g of x. It can be verified that under these operations f is a ring. For each a belongs to R, the map phi a from f to R defined by phi a of f is equal to f of a for f belongs to f is a ring homomorphism. Example 3. Set, the set of integers, is a ring under usual addition and multiplication. Set n is a ring under addition modulo n and multiplication modulo n. Consider the map phi from set to set n defined by for a belongs to set phi of a equal to R, where R is the non-negative remainder obtained when a is divided by n. Show that phi is a ring homomorphism. Solution: we first show that phi of s plus t equal to phi of s addition modulo n phi of t. Now, s t belongs to set can be written by division algorithm as s is equal to q1 into n plus r1 for 0 less than or equal to r1 less than n, and t is equal to q2 into n plus r2 for 0 less than or equal to r2 less than n. Hence, by definition of phi, phi of s is equal to R1, phi of t is equal to R2, and therefore, phi of s addition modulo n phi of t equal to R1 addition modulo n R2, which is equal to R3. If R1 plus R2 is equal to Q3 into n plus R3, equation number 1. Also, s plus t equal to Q1 into n plus R1 plus Q2 into n plus R2, which is equal to Q1 plus Q2 into n plus R1 plus R2, which is equal to Q1 plus Q2 into n plus Q3 into n plus R3, which is equal to Q1 plus Q2 plus Q3 into n plus R3. Hence, phi of s plus t is equal to remainder obtained when s plus t is divided by n, which is equal to R3, equation 2. From 1 and 2, we have phi of s plus t equal to phi of s addition modulo n phi of t. Now, we show that phi of s into t equal to phi of s multiplication modulo n phi of t. For the s and t noted above and phi of s equal to R1, phi of t equal to R2, we have phi of s multiplication modulo n phi of t equal to R1 multiplication modulo n R2, which is equal to R4, if R1 into R2 equal to Q4 into n plus R4, equation 3. Also, s into t equal to Q1 into n plus R1 into Q2 into n plus R2, a multiple of n plus R1 into R2, which is equal to a multiple of n plus Q4 into n plus R4, which is equal to a multiple of n plus R4. Hence, by the definition of phi, phi of s into t equal to R4, equation number 4. From equation number 3 and 4, we have phi of s into t equal to phi of s multiplication modulo n phi of t. Hence, phi is a homomorphism. Ideals. Let R be a ring. We partition R into disjoint subsets or cells such that these cells themselves can be viewed as elements in a ring where both addition and multiplication of the cells are the induced operations from R. That is, we define both operations by choosing representatives from the cell, adding or multiplying these representatives in R and defining the sum or product of the cells to be the cell in which the sum or product of the representatives is found. Both these operations must be well defined, that is, independent of the choice of representative from the cells. We first state a result from group theory. Lemma 1. If a group G can be partitioned into cells with the induced operation well defined, and if the cells form a group under this induced operation, then the cell containing the identity E of G must be a subgroup of G. Theorem 1. If a ring R can be partitioned into cells with both the induced operations described just above, the lemma well defined, and if the cells form a ring under these induced operations, then the cell containing the additive identity 0 of R must be an additive subgroup n of the additive group R under addition. Furthermore, n is an additive normal subgroup and have the additional property that for all R belongs to R and n belongs to n, both R into n belongs to n and n into R belongs to n. We express this last condition as R n subset of n and n R subset of n. Proof. Viewing R under addition as a group under addition, we know from lemma 1 that n must be an additive subgroup of R under addition. Since addition in R is commutative, every additive subgroup of R under addition is normal in R under addition. In particular, it can be seen that n is a normal additive subgroup of R under addition. We need only show that for R belongs to R, we have Rn subset of n and nr subset of n. Let R belongs to R. Now, R is in some cell A subset of R, and by our hypothesis that the induced cell multiplication is well defined, we can compute the products An and Na by choosing any representatives. Let us choose R belongs to A and 0 belongs to n. Then An and Na are the cells containing R0 equal to 0R, which is equal to 0. That is, An equal to Na is equal to n. Therefore, for all possible representatives n belongs to n, we have R into n belongs to n and n into R belongs to n. The following is a result from group theory. Lemma 2. If a group G can be partitioned into cells with the induced operation well defined and giving a group, then the cells must be precisely the left and also the right cosets of a subgroup G. In particular, every left coset must be a right coset. Theorem 2. If a ring R can be partitioned into cells with both the induced operations well defined and giving a ring, then the cells must be precisely the left and also the right cosets with respect to addition of the additive subgroup n under addition of R under addition, where n is the cell containing 0. Proof. Considering only addition, the ring can be regarded as additive group R under addition. Now, the result follows from lemma 2. The following is also a result from group theory. Lemma 3. If H is a subgroup of G and if the induced operation of coset multiplication on left or right cosets of H is well defined, then the collection of left or right cosets of H is a group under this induced coset multiplication. Theorem 3. If n under addition is an additive subgroup of R under addition for a ring R, and if the induced operations of addition and multiplication of cosets R plus n for R belongs to R are well defined, that is independent of the choice of representatives, then the collection of these cosets R plus n is a ring under these induced coset operations. Proof. Lemma 3 shows that the cosets form a group under the induced addition. The ring axioms involving multiplication follow at once, since we also compute products by choosing representatives, and since the ring axioms hold in R. For example, the left distributive law R1 plus n into R2 plus n plus R3 plus n equal to R1 plus n into R2 plus n plus R1 plus n into R3 plus n follows when we choose R1 belongs to R1 plus n as representatives and observe that the required R1 into R2 plus R3 belongs to R1 into R2 plus R1 into R3 plus n is true, since R1 into R2 plus R3 equal to R1 into R2 plus R1 into R3 by the left distributive law in R. The other distributive law and the associative law for multiplication follow similarly. Lemma 4. If H is a subgroup of a group G, then the operation of induced multiplication is well defined on the left or right cosets of H if and only if every left coset is a right coset. Theorem 4. If n under addition is an additive subgroup of the additive group R under addition of a ring R, then the operations of induced addition and multiplication are both well defined on the cosets R plus n for R belongs to R if and only if Rn subset of n and nr subset of n for all R belongs to R. Proof. The fact that if the operations are well defined, then Rn subset of n and nr subset of n follows immediately from theorems 3 and 1. Suppose that n under addition is an additive subgroup of R under addition, such that for all R belongs to R, we have Rn subset of n and nr subset of n. Coset addition is well defined. This can be seen by applying lemma 4 to the subgroup n under addition of R under addition. For multiplication, we must show that a product R1 plus n into R2 plus n computed by choosing representatives is well defined. It is no loss of generality to take as two representatives of R1 plus n the elements R1 itself and R1 plus n1 for n1 belongs to n. Similarly, let R2 and R2 plus n2 be two elements of R2 plus n. We must show that R1 plus n1 into R2 plus n2 is in the same coset R1 into R2 plus n as R1 into R2. Now, R1 plus R1 into R2 plus R2 equal to R1 into R2 plus n1 into n2 plus n1 into R2 plus R1 into n2 by the distributive laws in R. The assumption that Rn subset of n and nr subset of n implies that R1 into n2 belongs to n and n1 into R2 belongs to n. Viewing n1 as an element of R, we have n1 into n2 belongs to n1 n and n1 n subset of n. So, R1 into n2 belongs to n also. Then, since n under addition is an additive subgroup of R under addition, we see that n1 into R2 plus R1 into n2 plus n1 into n2 belongs to n. So, R1 plus n1 into R2 plus n2 belongs to R1 R2 plus n. This completes the proof. It is now clear that these special additive subgroup n under addition of a ring R having the property that Rn subset of n and nr subset of n for all R belongs to R are going to play a role of basic importance in ring theory, analogous to the role of normal subgroup in a group. Note that the conditions Rn subset of n and nr subset of n imply in particular for R belongs to R that n is closed under the multiplication of R. Thus, we can consider n with the induced addition and multiplication from R to be a subring of R. Remark. Not every subring n of every ring R satisfies the condition Rn subset of n and nr subset of n. For example, Q subset of R, but pi into Q not a subset of Q. Definition. An additive subgroup n under addition of a ring R satisfying Rn subset of n and nr subset of n for all R belongs to R is an ideal or two-sided ideal of R. A subgroup n under addition of R satisfying Rn subset of n for all R belongs to R is a left ideal of R. and one satisfying NR subset of n for all R belongs to R is a right ideal of R. When we refer to an ideal, it will always be assumed to be a two-sided ideal. Remark: an ideal is to a ring as a normal subgroup is to a group. Example 4. Every ring R has two ideals, the improper ideal R and the trivial ideal 0 set. Quotient rings. Definition: if n is an ideal in a ring R, then the ring of quotients R plus n under the induced operation is the quotient ring or factor ring or residue class ring of R modulo n and is denoted by R by n. The quotients are residue classes modulo n. Example 5. Consider the ring Z of integers. The only additive subgroup of Z under addition are the subgroups n set. Clearly, if R is any integer and m belongs to n into Z, then Rm is equal to m into R is again a multiple of n. That is, if m is equal to n into S, then R into m is equal to m into R, which is equal to n into S into R, and n into S into R belongs to n set. Thus, n set is an ideal and the quotients a plus n set of n set form a ring Z by n set under the induced operations of addition and multiplication. Example 6. Show that the rings Z by n set and Zn are isomorphic. Solution: define for A and B in Zn the products A into B modulo n to be the remainder when divided by n of the usual product of A and B in Z. The map phi from Zn to Z by n z given by phi of A is equal to A plus n z is clearly a one-to-one onto map. Also, phi of A under addition modulo n B is equal to phi of A plus phi of B and phi of A multiplication modulo n B equal to phi of A into phi of B. Hence, phi is a ring isomorphism. Then Zn under addition and multiplication modulo n may be viewed as Z by n z renamed. We shall often identify Z by n z with Zn by means of this isomorphism phi, which is a natural or canonical isomorphism. Example 7. We know that Zp is a field for P a prime. Also, using example above, Zp is isomorphic to Z by Pz. Hence, the quotient ring Z by Pz is a field. Example 8. It can be verified that the subset n is equal to Z03 of Z6 is an ideal of Z6. And Z6 by n has 3 elements 0 plus n, 1 plus n and 2 plus n. It can be seen that Z6 by n is isomorphic to Z3 under this correspondence 0 plus n to 0, 1 plus n to 1, 2 plus n to 2. Example 9. Consider the ring Z cross Z. If n is equal to Z of all ordered pair 0 n, n belongs to Z, it is clear that n is an ideal of Z cross Z and that Z cross Z by n is isomorphic to Z under the correspondence ordered pair m0 plus n to m, the residue classes being of the form ordered pair m0 plus n where m belongs to Z. Remark: Z cross Z is not an integral domain, but Z is an integral domain. The above example illustrates that a quotient ring of a ring may be an integral domain even though the original ring is not. We have noted that R and Z0 are ideals for R. For these ideals, the factor rings are R by Z0, which is clearly isomorphic to R. A proper non-trivial ideal of a ring R is an ideal n of R such that n not equal to R and n not equal to the 0 space. Theorem 4. If R is a ring with unity and n is an ideal of R containing a unit, then n equal to R. Proof: let n be an ideal of R and suppose that u belongs to n for some unit u in R. Then the condition R n subset of n for all R belongs to R implies if we take R equal to u inverse and u belongs to n, that 1 equal to u inverse u is in n. But then R n subset of n for all R belongs to R implies that R into 1 equal to R is in n for all R belongs to R. So, n equal to R. Corollary: a field contains no proper non-trivial ideals. Proof: since every non-zero element of a field is a unit, it follows from theorem 4 that an ideal of a field F is either the 0 space or all of F. Let us summarize this session. In this session, we have briefly discussed ring homomorphisms. A discussion on ideals and quotient rings are also made. Expect you enjoyed this session. Now try to answer the following questions. Question number 1. Find all ideals n of Z12. In each case, compute Z12 by n, that is, find a non-ring to which the quotient ring is isomorphic. Question number 2. Give addition and multiplication tables for quotient rings 2Z by 8Z or 2Z by 8Z and Z4 are isomorphic rings. Question number 3. Give a subring of the ring Z cross Z that is not an ideal of Z cross Z. See you next time. Till then, goodbye.